Welcome to the May installment of our Spring 2022 webinar series sponsored by NIST. Today we have extracting case-specific information from validation studies. Our presenters today are Steve Lund and Hari Iyer. Steve graduated from St. Olaf College before getting his PhD in statistics from a little place I like to call home, Iowa State University. Hari graduated from St. Xavier's College in Mumbai before finishing his master's and PhD degrees in mathematics from the University of Notre Dame. Both are currently part of the Statistical Engineering Division at NIST and have been phenomenal contributors and advisors to CSAFE over the years. Gentlemen, I will let you take it from here.
Thank you, Anthony. This is Hari. My colleague Steve and I are going to talk about extracting case-specific information from validation studies. I also want to thank CSAFE for putting together this webinar in particular. I'll jump into an example right away to motivate the topic. Suppose we have a crime scene DNA sample, and it's judged to be a 4-person mixture, each donor contributing approximately 1:1:1:1 ratio. Suppose the total template amount is around 100 picograms, and the sample appears to be somewhat degraded. Okay. The sample is compared with the defendant's profile. So sample is Q, defendant profile is K. Two propositions, mutually exclusive and exhaustive, are considered. HP is the defendant's DNA is in the crime sample. HD is that it is not. Typically, the analyst would manually examine the electrophoregram and make some decisions and use a ProbGen software system and eventually arrive at a likelihood ratio assessment. Suppose that in this case, the likelihood ratio turns out to be 100,000, or log base 10 likelihood ratio is 5. The expert would testify the evidence is 100,000 times more likely under HP than under HD. Many people would hear this as HP is 100,000 times more likely to be true than HD is, which of course is the transposed conditional, but that's a topic for discussion on a different day. The question we are interested in, and people should be interested in, is to what extent can the reported LR be supported by empirical data? So the reported LR in this case, not overall general performance, etc. So in this case, the casework sample is deemed to be a 4% mixture, 1:1:1:1 ratio, somewhat degraded template amount. And what we need are the distributions of the likelihood ratios under HP true scenarios, under HD true scenarios for ground truth known samples like the case sample. So how does the method behave in cases like this, not some overall general performance? So what we expect to see if we have appropriate data, ground truth known data, is that the ratio of the densities under HP and under HD corresponding to the reported LR of 100,000 should be about 100,000. That's what the expert is testifying to. So you ask, are such data available? Can we do any sort of investigation of the degree of support for the offered opinion? For illustration, we picked the ProveDit database. The URL is given here at the bottom of the slide on the left. We found 64 samples that were roughly like the case sample. And we have the HP true LR values for those cases and HD true LR values using a ProbGen software. And the histograms of those are shown in the picture. The red is for HP true and the green is for HD true. And the scale is log base 10 LR on the x-axis. The likelihood ratio we are interested in is the probability of the evidence given HP and probability of evidence given HD, the ratio, where E here is the opinion that LR is 10 to the 5. So this is the evidence presented, the information presented by the expert, and we want to see to what extent the empirical data would support that. So one way of approaching this is fit distributions. So this is HP true data. I fitted a Gaussian distribution. You have to check and see that this is a reasonable model, and people have their own favorite diagnostic checks. And the one for illustration that we are using here is the Kolmogorov-Smirnov test, or the confidence band shown here. So the cumulative distribution function associated with the fitted density, we check and see that it falls in the Kolmogorov-Smirnov band. And the dots, the black picture is the empirical cumulative distribution function. So here we conclude, yes, this is not an unreasonable model. And then you do the same thing for HD true data, fitted density, Gaussian density here for illustration. Check to see, if it's reasonable or at least not unreasonable. And diagnostic checks pass. Then you use those models to assess the density values at the point of interest, which is log base 10 LR of 5 here. So you take that height from HP, take a small height here from HD. I've zoomed in to show you what the tail density value looks like. And those numbers, the numerator density is 0.138, denominator is shown here. The ratio is 501.5. So the presented LR was 100,000. Our own assessment using performance data available from validation studies is that LR of 501.5 could also be supported by the empirical data. And what you really want to do ideally is not just look at one model fit, because that's what people often do, is fit Gaussians and do some diagnostics and take the result and interpret it. What you really want to do is look at what other models could also be deemed plausible, and what are the answers when you use those other models. Now, this picture shows multiple Gaussian models that could all be deemed reasonable for the HP data and for the HD data. The only purpose of these slides is to show lots and lots of models would pass the diagnostic test. Okay. And this picture shows for the HD true distributions, when you consider a lot of possible plausible models, the density value at the point of interest, which is log LR of 5, can be large or small, and a whole range of possible values depending on which model you chose. And that's going to affect the resulting LR value that you arrive at. So we wanted to approach this question of plausible range of LR values in a systematic way. Ideally, what one has to do is select a distribution that's inside the KS band for modeling the HP data. Similarly, for HD true data, evaluate the densities at the point of interest, take the ratio. That would be one plausible LR value supportable by available empirical data. Now you do this for all possibilities. Basically, you're talking about infinite number of possibilities. That's not practical, so you do this for as many as your algorithms might be able to solve, and find the range of LR values obtained. Our point of view is that this range is what we can provide based on our expertise. When we pick one value from this range, or even a narrow range of values based on some incomplete uncertainty analysis, and communicate this to decision makers, we, meaning statisticians or whoever is doing the statistical analysis, we're injecting non-professional opinion, not related to expertise, into testimony. So our claim is the expertise takes you as far as identifying a range of LR values, but no more. So what's our approach to actually implement this idea? We consider two situations. One situation, we allow for any distribution that's inside the KS band as a plausible distribution, and calculate the LR range by examining all possible distributions in this class. But maybe people would think it's more reasonable to restrict the class of distributions. So we also look at distributions that are unimodal. And that includes lots of familiar families: Gaussian, T, chi-square, gamma, log normal, Pareto, and so on. So my focus today is going to be on this, on this unimodal case. And to actually have an algorithm that can allow for the calculation of the LR range, we represent univariate continuous distributions by linear spline PDFs using a sufficiently fine grid. So you can very well approximate just about any density function in this manner by just taking a finer and finer grid. The heights of the probability density function are the variables denoted by F1 through Fn, where n are the number of grid points. For unimodal distributions, these Fs should satisfy many constraints. Fortunately, these are constraints that are linear in the unknowns. And the objective function would be the value of the density function at the point of interest. In this case, it could be log LR of 5. We would be interested in maximum achievable density value as well as the minimum achievable density value while remaining unimodal and while remaining within the KS band. Okay. The constraints can be written down mathematically. This delta I is the spacing between successive grid points. This constraint says that you have a density, the area under the density is 1. The unimodality constraints are shown here. Our definition of unimodality is that the density function has no more than 2 inflection points. So this is a bit stronger than the usual definition of unimodality. And the 2 inflection points are denoted by index A and index B. And the constraints change depending on what region of the support interval that you are in. The optimization problem is the 2-stage optimization problem where the outer layer is a nonlinear optimization in 2 parameters, and the inner layer is a linear programming problem in any number of parameters or variables, depending on how fine a grid you take. The Kolmogorov-Smirnov constraints are also linear in the unknowns. So the point of this is that this is a feasible problem that can actually be implemented and solved. So for the example problem, one of the extreme distributions we fitted is shown here. Its density is here. This is HP true case relevant validation data The fitted density is shown in blue. And at the point of interest, log LR of 5, the value of the density is 0.051. Similarly, you consider the largest possible density value for the denominator of the likelihood ratio. Here is the density, and the value at point of interest is 0.020. So what is it that we have thus far? So for HP true data, the minimum value that could be justified for the numerator of the LR is 0.051. The denominator value maximum that you could justify is 0.020, and the ratio is 2.55. So that's LR, not log LR. So what this is saying is that based on the empirical data that's available, that's case similar data, you could support a likelihood ratio value anywhere between 2.55 and infinity. Now it turns out that I'll summarize what we found using Gaussian models and using the more thorough search. Using Gaussian models, we found an LR of 505. Expert says LR is 100,000. The range analysis says LR can be anywhere between 2.55 and infinity. What I mean is any value in that range can be supported by available empirical data. Now, expert's value is in the range, but any other value in this range is also consistent with the validation data that's available. And which value you report from that range will impact, makers will decide. So this is an illustrative example. In practice, labs, here I'm focusing on DNA, by the way, but the concepts will apply in any forensic discipline. Labs have limited validation data. Typically from my knowledge of what happens, 100 to 200 internal validation data would be available that covers a range of possible number of contributors, template amount, etc. So if you look for case similar validation sample, you would find very few or sometimes none. And it also depends on what you mean by similar, how similar is similar. So this is an issue, and Steve is now going to talk about how you can leverage available validation data to extract information about a case-specific scenario.
Thank you, Hari. As we try to get to a case-specific scenario, the reason this is a challenge is because there's many things that could impact the distribution of method outcomes or how a given method performs. One easy way of thinking about this is that for any discipline, often there are some cases that are considered to be easier than others. And so when we say easier, that means we expect the distribution to be different across these factors. So if we have a cartoon example here, maybe the reds are representing HP true situations and blue are representing HD true, but that's not the only difference that affects the output of the system. There's also some notion of something like a case difficulty. And what matters is not the average across this full spectrum, but if this purple dot is representing the current case, we would be most interested in what is the behavior of the method in situations just like this. And if you happen to have a lot of validation data in situations very similar to the case at hand, that's great. Unfortunately, that's usually not the case since there are so many different possible scenarios and data is really expensive. So this raises the question of how can data from other situations help inform the behavior. One approach to doing this is to attempt to account for and eliminating differences in method behavior, what also might be known as biases across the various scenarios using statistical modeling. So the general approach for this is similar to kind of any statistical modeling, which includes identifying a set of factors that might be expected to affect the distribution of outcomes, to fit a model to estimate the effect of those modeled factors, and to use differences between the modeled values in different scenarios to estimate what a result that was actually measured in one scenario would have been like if we had measured it in the currently considered scenario. So I'll start off with a really simple cartoon example. Suppose that the black data or black circles are representing validation study results, say from scenarios representing the prosecution perspective across a range of a given factor. Here we can clearly see there's a trend that this score is tending to increase as the factor increases. So that is, we see that it's changing as a function of the factor. And if we go to where the current case, suppose that's represented by this blue circle here, we don't have any validation data in this particular case. So if we were looking strictly at our validation set for what does it say about this exact case, there's no information there. But one could attempt to apply a model that describes tendencies of how the score distribution is affected by factor using a model. And then we can look to say, so this now is what's called a residual. So each of these heights, rather than being the original score, is just the score minus the value of the model at that given value of the factor. So it's just taking these distances between the center of the black circles and the red line. That's what's known as a residual. And now I say when we look at residuals that there isn't such an obvious trend between those residuals and the factor. And so if one then said, oh, well, these are more or less constant across a factor, the distribution is stable across this factor, then we could use these observed values and treat them as if they had all come from the currently considered case scenario. Then if we look back onto the score setting, we're just mapping those residuals, again, centering them around the corresponding position of the red line. And that would give us a collection of data that we could use and apply the LR range analysis. So I just wanted to mention, since this will involve modeling, you could fit different models to this data set. Even in this simple example, you could fit something other than a perfectly straight line. And that would, of course, impact how we translate the results observed for one level of a factor back to a projected result that would be observed for the currently considered level of the factor from the case result. So this is another form of modeling uncertainty, and we will not get into addressing this type of modeling uncertainty in this talk. I think there's enough content as it is. So taking those projected points now gives us kind of a distribution that we could work with. So this now is a histogram of those 20 points having been mapped from where across the range of this considered factor back to the scenario for the current case. And then this would enable us to apply the range analysis that Hari discussed. So I'd like to move out of the cartoon example and into kind of a prototype implementation. Before I do that, I just want to mention the disclaimers that, as we mentioned, certain software is in here. This does not represent a recommendation or endorsement by NIST, nor does it imply that those are the best tools to use for the purpose. And then also the perspectives we're presenting here are our own and don't reflect any official NIST policy or necessarily represent the viewpoints of anyone other than Hari and myself. Okay, so for the validation factor space prototype, like Hari had mentioned, we were working with the ProvedIt database. So this is a collection of electropherograms from a variety of mixtures, including 2, 3, and 4 person mixtures, different mixture proportions, template amounts, and degradation levels. And each of the obtained electropherograms was compared to reference profiles for each of the actual contributors that were used to make the mixture, as well as the same number of random non-contributors. So this has a total then of a little over 2,500 comparisons, and it's evenly balanced between contributors and non-contributors. And these electropherograms were analyzed using StarMix. The analysis is described in this paper shown here by Sarah, Hari, and Pete. So you can check out those details if you'd like to see where specifically the values I'll be using are coming from. But so the response then is the output LR value from StarMix. But we know that the distribution of LR values provided by StarMix will vary from one scenario to another. Whether you have high template, high quality, low number of contributors, like 2 contributors, will have a different behavior than situations where you have very little DNA that's degraded and there's a larger number of contributors, like 3 or 4. So we want to try to define these factors so that we can implement a factor space analysis here. And to do that, we'll be looking at information that is output by StarMix when it analyzes the question profile. So one of the types of output that StarMix provides is an estimated template amount for each of its perceived contributors. So it is also estimating the number of contributors. Here in this example, it's estimating 4. And then for each of those, it tries to do a deconvolution that estimates how the template amount for each of those 4, converts that to a mixture proportion, gives some information about degradation. It also does a deconvolution in trying to identify what genotype distribution applies to each of the contributors. So this is just the result for the first contributor in the estimated mixture. And it breaks it down by locus here. Just a small subset of the full table is shown. But so for this first locus, it is reporting results for a variety of potential genotype combinations that this contributor profile may have at this locus. For instance, 1516 is given a weight of 39 or 31.99%. So we end up treating this as if it is a likelihood for this genotype at this locus for this contributor, which then lets us, let me go to compute likelihoods for a given reference profile under each of the contributors. So suppose that a reference profile that we're comparing actually had genotype 1517 at this particular locus. To compute a corresponding likelihood for this, given the deconvolution table from StarMix, we go and can find 1517 is one of the genotypes present in this table, and it had a weight of 10.5%. But then there are also these things that are Qs. So Q is a potential for a dropout or an unknown, which in this analysis we treat as kind of like a wild card. So if the reference profile is matching the fixed genotype component as well as a Q, we consider that also a potential way to have observed this genotype in this mixture. So we're also adding in the things that work when combining with a wild card. So that would give the likelihood for the reference genotype at this locus. If we have 0.105 here, from 0.028 here, 0.0144 here, and 0.0035 here, add those up, and that gives us a combined weight of 0.152. So we could definitely refine this further by, instead of treating Q as a full wild card, that we could refine that using a marginal allele distribution across a population of interest. That's not implemented in the prototype illustration here. But I also want to talk about one other aspect quickly about the contributor profiles, and that is another factor relating to the queues. So queues are the potential of for dropout, and this is also something that speaks to sample quality. So we wanted a measure of the amount of dropout potentially present for a given contributor. And for that, we're taking what I'll call the expected number of dropouts. So for each time there is a dropout, we look at the weight given to that combination that contains the queue and add them all up. And for the combinations that have both queues, we count that twice. So for our expected number of dropouts, we had 0.032 from here, 0.028 from here, 0.014 from here, and 0.2 times 0.0035. So from this locus for this contributor, the estimated contribution to expected number of dropouts is 0.08. Now for both likelihood and the expected number of dropouts, we consider all of the locuses at a given time. For the expected number of dropouts, we're just adding this expected value from one locus to another. And for the likelihoods, we are considering the product of the locus specific likelihoods to give a likelihood for the complete reference profile. So using those locus specific likelihoods, we then get a likelihood for the complete reference profile, like I was just saying, taking the product across the locus. And then for our factor space, we are using a equal prior closed population posterior as a way to weight factor values across the different contributors in the mixture. So this is not a ultimate characterization of the probability that the reference profile is this particular component in the mixture. Rather, it is if the person were in the mixture, if the reference profile were from a contributor whose material is in the mixture, which of those contributors would it be? And the equal prior part is just saying each of the contributors identified by star marks are given equal prior beforehand. So that means that we're just taking, essentially weighting by the likelihood of the reference profile under the distribution for each of the contributors. So where do we use those? Well, so again, like I was saying, in assuming that the reference profile is from one of the contributors, then what is the condition of its component of the mixture? So if one of the contributors in the mixture was high template, but the contributor most closely corresponding to the reference profile is a very low contributor, we didn't want to describe that sample just as high or low or as high and low. We wanted to say, well, for this particular reference sample, is its component high or low in the mixture? And then separate that from what are the conditions of the other components of the mixture. And so we use this posterior weight across contributors to compute an expected template and the number of dropouts for the reference profile, and then use 1 minus the posterior as a way of trying to characterize what's happening with the other components in the mixture. So then for the modeling approach, we are taking the log 10 value of the likelihood ratio returned by StarMix as our response. And just in the implementation that was used for StarMix, some of the loci occasionally produced a value of 0 in likelihoods for a reference profile, which when you take the product makes the overall likelihood 0, regardless of what happens from other loci. And this happened in 525 HD occurrences out of a little over 1,200 and 2 HP occurrences. And for this illustration of the prototype, we did not dig into assessing, confirming, or updating whether those should be 0 or not. They're just removed from this analysis at this point. Then with the remaining data, we use a random forest model to relate the factors that I just discussed to these log 10 LR values, and did this separately for the true contributor references and the non-contributor references. So here's the log 10 value reported by StarMix. That's on our y-axis. This top panel here is corresponds to HP true as the ground truth for the mixture. So this is true contributors. And the lower panel represents HD true. So truly non-contributors. And then these are each of the columns corresponds to one of the 5 factors that I just had discussed. So first was number of contributors in the mixture, the expected number of dropouts computed from the perspective of the reference profile, the expected number of dropouts among the other components of the mixture, the template amount for the other components of the mixture, and the template amount for from the perspective of the reference profile. And so if we do just kind of a sanity check, each of these factors is kind of behaving in the way you would expect. The HP or the log LRs tend to get closer to 0 as you add more contributors into the mixture. As the expected number of dropouts increases, so you start to get some worse and worse quality or less and less template, kind of a combination of those two. As that increases, then also you tend to get log LR values getting closer to 0. And as template increases, then you tend to get more compelling LR values in general. So let's see here. And so this is analogous to that first plot of the linear regression, where there are clear trends in the response as a function of the candidate factor. Here we can see that the distribution is changing across these factors. And so we use the random forest model fit separately to the data from the top and to the data from the bottom to arrive at predictions to try to adjust those to see if we can get to something more stable. And so this is now looking at residuals from the random forest fit, and it's certainly more stable than it was. It's not perfect, because we can still see that there's potential trends here, in particular related to template, but those trends are certainly less severe than they were before. So we have substantially stabilized that distribution. If we now look, instead of as a function of template, number of contributors, or number of dropouts, if we just use the value predicted from the random forest to look at our data, we can see another type of trend becoming evident. And that is, it looks like the spread of the residuals is smaller for the HD true scenarios when it's predicting a value, a log LR value near 0. So this is kind of for the more tricky cases who tended to get a tighter grouped behavior, or so less variability in the output from StarMix. And so this is also a component of a distribution that we can adjust for. To do that, we looked at the absolute value of the residual as a local measure of scale, like analogous to standard deviation, and fit a smoothing trend to those, and then now divide each of the residuals by its corresponding value from this smoothed profile to get what we call a scaled residual. And so this is looking more stable as a function of the random forest prediction than the original residuals. And this is what we are then using to apply the LR range analysis. So for each of the two ground truth states, the HP true and the HD true, we now have a collection of data that we can work with and apply the LR range analysis. And I'll show the results here. So remember that the first component of this is to estimate a range of density values that one could achieve for each of the corresponding residual values. So that's what's shown here. The scaled residual value is on our x-axis here. And then there are two curves shown for the HP and the HD true scenarios. The cyan color one is representing what was the maximum density found using the range analysis Hari described previously. And these spikes and plateaus are regions near the center of the data where the density could spike off to arbitrarily high. So I've just, for the purpose of plotting here, have cut that off at a value of 100,000. And similarly, the plateaus off to either side in the tail are, the red curve now is corresponding to what is the minimum value that the optimization could find for that density. And the plateaus here on these red curves correspond to positions where the density could shoot all the way down to 0. So on a log scale, that wouldn't fit well on this plot. So just put in a cap for that as well. So things that are falling in the flat region for the red means it could be a value as low as 0. Things falling in the flat region here for the cyan color means it could be a value as high as arbitrarily high, really infinite, while still satisfying the unimodality constraints and falling within the KS bands for the provided data. And so we will use this now to characterize what is an LR range, what is a range for a given case. So suppose our case example had 3 contributors where the expected number of dropouts for the reference profile was 4.3 and 3.3 for the other components of the mixture, is a template amount of 79 for the reference profile and an average template of 159 for others. So this now describes the feature set for the currently encountered case. And we don't know whether that's HP true or HD true. We just know what are the characteristics of the question profile, and then can send those features through the predictive models to get what, based off of the validation data set, would we expect to have seen if it were an HP true. So if this were a true contributor, according to the HP true model, when you put in the values corresponding to these red lines indicating the factors and the black dot, or the factors for the currently considered case, and the black dots are representing the validation data available to you, it suggests under the HP model that we'd expect to see on average an LR of about 100,000. And then also when we looked at the adjusting for the scale, the variability around that, that average is characterized by a 2.22 scaling factor. Then we can also take those same values of the factors, plug it into the model for the HD true validation data, which is now in this bottom panel, the black dots. Those are the values from our HD true reference comparisons. And when we send the values corresponding to the current case through there, we get a prediction that if this were an HD true case, we would expect to see a log 10 LR of -7.3 for this case. And then that had a scaling factor of 3.09. So, and if we had a different case, right, you can put in different values of these features. So instead of having 3 contributors, you have 2 contributors and a different number of expected dropouts. Regardless of what your current case is, we can still obtain the predicted values for from the random forest model corresponding to what would you guess for an average log LR under an HP true scenario and its scaling factor, and what would you expect to see for a log 10 LR if this were an HD true scenario and the corresponding scaling factor. So that means we can take the system output. So suppose that the LR here were 1 million, and we can subtract or we can construct our scaled residual by subtracting the corresponding prediction from the random forest model. So that's the adjustment of the mean, and then divide by the scaling factor corresponding to that mean to find our position in the scaled residual space. And since the means and scaling factors differ under the HP scenario, right, the behavior of the system for HP true cases differs from that for HD true cases. We have to construct the scaled residual separately for each of those two scenarios, but we can find our corresponding position in each of those spaces, and now can consider the range of the likelihood ratio for our data. So for the HP true scenario, we have a scaled residual that's somewhere close to -1. And that is still in the range where the density for the scaled residuals can shoot up towards infinity. So the maximum the numerator could be is infinite. And if we're trying to get to the maximum LR, we would then divide that value by the smallest we could get in the HD true, which over here is shown to be 0. So the upper bound is infinity divided by 0 is infinite. So we can't really place any sort of cap on how high the likelihood ratio could be, but we can get useful information about how low it could be. So for that, we would take the smallest value we could achieve for the density in this currently considered case, and divide that by the maximum density that we could get for the currently considered case under the HD true scenario. And so that's where this value of 14.8 comes from. In the background, there's a scaling factor happening to the densities to make sure that they integrate to 1. Bottom line was here for a system output of 1 million. The LR range analysis would say that the LR is at least 14.8 and could be as high as infinity. If we go to, instead of considering a system output of 1 million, if we consider one of 1 billion, it's still kind of in the same range where the numerator density can shoot off to infinity and is capped below. And that ends up leading to a lower bound of 31. And then if we go up again to a value of a trillion. So now, interestingly, the lower bound for the LR has dropped. And that happens because you can see here now that the curve representing how small could the density be for the numerator in this likelihood ratio is starting to drop fairly rapidly as we start to get outside where the values typically fell in the scaled residuals. So we see this start to drop off. So even though the nominal LR has increased from the system, if we start to shift outside of what was expected from the system based on the validation data, the lower bound can actually become less and less as you get higher and higher or more extreme likelihood ratio values. And one way of thinking about that is when you start to get in the tails of both distributions, so both the HP true distribution and the HD true distribution, the ratio of tails is not something that is well characterized or well bounded. And so our uncertainty really starts to explode as we drift out there. And if we push this to even a further extreme now of going out to a quadrillion, then we're outside of the range where the lower bound of the density in the numerator is kept above 0. So this is saying, given the data that we have, and for this particular type of case, we don't have evidence to suggest that we, for sure could ever see a value this big under HD. So it could be as small as 0. But of course, we don't know that it's 0. That's just the lower bound. So the upper bound is still something larger than 0. And so now if you look at the range for the ratio, you get a value larger than 0 divided by 0 gives you an upper bound of infinity. And on the lower bound, you get a value of 0 divided by something bigger than 0. And that gives you a lower bound for the likelihood range of 0. And so that's why I say it becomes unbounded as you start to get extreme values, where extreme is in the context of the expected distribution for the currently considered case. And just wrapping up, you can go in the other direction too. If the system had output a likelihood ratio of 1/1,000,000, then the LR range analysis analogous in the opposite direction. Rather than saying it could go up to infinity, it could go as low as 0, but it's not bigger than 0.23 for this system. And if you push that farther, considering a likelihood ratio of 1/1,000,000,000, this drops it down to something of 0.028. And just as before, if you go too extreme outside of the range that's kind of expected for this data, even as you start to push to really, really small values, you start to get values in the LR range analysis that moderate that, pulling it back towards 1 as you start to consider the ratio of tails. So some additional considerations. One, this is a prototype implementation. It is based on real data, but we're only considering a single model here, just the application of the random forest for the particular factors that we've chosen. And it'll be important to acknowledge the uncertainty in the mapping. So when we're converting or moving the results from one scenario to the currently considered case, that's dependent on the model predictions. And we need to capture some of the uncertainty in that modeling to fold that into the range analysis. And in particular, that might get highlighted, for instance, of what if you had a bunch of validation data from scenarios that were very different from the current case. Like maybe you have a ton of validation data in footwear impression comparison, where the impressions are coming from athletic shoes, but now you have a case in a high-heeled shoe. So on a simple cartoon example, that might be illustrated something like this. You have your validation data way over here. You have a current case, and then we'll throw a bone of having one validation observation over here. In this instance, there's pretty enormous modeling uncertainty in trying to figure out how to adjust validation data to correspond to the currently considered case. For instance, you could imagine there being a diagonal line kind of from the center of this blob down to here, and we just slide it along that diagonal line until we get to the corresponding position, like we did with the initial linear regression illustration. But you could also imagine that the mean stays the same and just the variability in the distribution changes. So there's a huge amount of uncertainty here, and that's something that would need to be accounted for, especially in instances where the current case is relatively extreme among the collection of validation cases that have been collected to date. And then additionally, how do we check aspects of the distribution other than the ones that we were explicitly adjusting for using modeling? So in the random forest illustration, you're adjusting for the mean using the random forest, and then also adjusted for the scale. But there are other aspects of the distribution that could be changing as well. And so one thing we've toyed around with that, but don't have time to illustrate today, is to initially restrict yourself to circumstances closest to the currently considered case and apply this process for those instances, and then progressively expand out to cases that are farther and farther from the circumstances of the current case, and at each step checking to see, is that new set of projected results for the current case, are they still matching the distribution that you had from the already considered case, those from validation sets closest to the currently considered case. So basically trying to monitor for changes in the distribution as you expand out from the currently considered case. Yeah, this is more of, again, a prototype. We're interested in hearing back from the community about the utility of this or suggested improvements or alternatives. So we look forward to hearing from you. Please don't hesitate to email us after the talk or to submit questions. So thank you very much for your attention, and we'll happy to stay on to answer some questions. So there is a question of where did your HD True samples originate? Were they simulated?
No, they were not simulated. They were taken from the population data that NIST has. The 1,036 unknown, unrelated, random people.
Yeah, thank you for this interesting presentation. Any advice for students wanting to get into statistical forensics? So our particular twist on statistical forensics would be mindful of the influence of modeling assumptions, and that can make things more computationally challenging, but also makes things, I think, more interesting. And so one way of thinking about that, as Hari often says, is assumptions are kind of an if-then statement. If these things are true, then this particular output would hold, or this answer would hold. And it's a challenging and interesting question to try to consider. What is the range of if conditions that one should be considering? And how does that affect the range or distribution of the then statements?
Stephen, Hari, thank you again for joining us and providing your presentation and sharing your information with the world here. And that will live on in the recording. Thank you all for joining us, and we hope you have a great day.